This is problem 2-76, it's on page 103. An oil pump is drawing 35 kilowatts of electric power while pumping oil with a density of 860 kilograms per cubic meter at a rate of a tenth cubic meter per second. The inlet and outlet diameters of the pipe are 8 centimeters and 12 centimeters respectively. If the pressure rise of oil in the pump is measured to be 400 kilopascals and the motor efficiency is 90%, determine the mechanical efficiency of the pump. Let's try to wrap our heads around this. Let's draw the system. I don't have it drawn in my solution, but I'll copy it down. In fact, it's worth copying the figure directly. So let's just do this. So here's the motor. And that's what's drawing power in the form of electricity at the rate of 35 kilowatts. Now that motor is coupled by a shaft to a pump, and your author has drawn the pump this way, so I'll copy it. Of course, its axis is off, but that doesn't really matter. We're just doing energy analysis, so we don't really care about the mechanical details of how this thing works. There's another mechanical detail that I'll point out at the end of the problem, but for now we'll just solve it. The diameter at the entrance is 0.0812 meters, and the diameter at the exit is 0.12 meters. The oil is flowing at a rate of 0.1 cubic meters per second. What kind of symbol do you think we should use for this flow rate?
E dot.
V dot, that's right, that's what we're going to use. This is not M dot, this is a volumetric flow rate, so it's V dot. Of course, that just goes through here and has the same flow rate. Okay, so the pressure rise, in other words, the delta P across this thing, I should draw it in this direction because it actually increases in that direction, is 400 kilopascals. Anything else that I'm missing? Oh, the density of the oil is 860 kilograms per cubic meter. So would that oil float or sink on water?
Float.
You know it would float because oil floats, but how do you prove that?
Because water is 1,000 kilograms.
I just thought water is about 1,000. This is 860, so this is less dense than water. I want you to start to get a feel for some numbers and what they mean by comparison to common stuff. That's why I go over these things. Okay, we were told the motor efficiency is 90%. Now, what does a 90% efficiency mean on the motor? Efficiency is just a ratio, right? Desired output over required input. So what does it mean?
It means that what we're getting at, we're putting in 35,
Right?
but whatever is over that is 90% of 35. Our output is 90% of whatever our output is.
Okay, so basically the motor is converting energy from one form to another, and only 90% of the energy that came in, which you correctly recognized as electricity, goes out in another form. What form does the energy go out of the motor in?
Flow, shaft power,
Shaft power, right? It's not the pump. We haven't talked about the pump yet. We're just talking about the motor, right? So the efficiency of just the motor itself is 90%. In other words, the power flow rate out in the form of shaft power over the required input of electrical power, that ratio is 90%. Where does the other 10% go? Because another form of energy flows out of this motor if it's at steady state. So where does it go? Where does it? Heat, right? So heat loss. Friction ultimately turns into heat. Okay? So inefficiencies. All right, so that's what we, now the other question is, well, what's the efficiency essentially of the pump? That's, let's see, yeah, determine the mechanical efficiency of the pump. Well, let's start off by finding out, well, I guess I should follow the solution that I made, shouldn't I? I don't want to. I don't feel like it. I just want to work it for you.
He just wants to break the rules.
Well, sometimes I think that if I solve it in a different way from the way I've written it out in the PDF, it'll help you. So, I don't know. I'd like your feedback on that, actually. I'd like to know what you think of that. Should I just follow it directly, or?
When I looked at the homework one online, it
I'm sorry? When you looked at one
first
online?
homework,
Yes.
I said like the solution, I tried to watch the video or PDF, it was just blank.
It was blank?
When I tried.
Okay, so that's 2 people. We'll look into that a little later. Good question. But I'm trying to get them posted.
I like 2 different ways, because you can do a lot of these in more than one way. Or your order can be different, so I like
Yeah.
to see that. I like it.
All right. Well, we'll see how it goes. All right, so what I would do to start off, or maybe I don't remember what I did when I saw this. What I would do to start off, we want to find the efficiency of the pump, right? So I'd like to get some equation so I can plug it in. A lot of times you're trying to solve a problem like this. And one of the questions I get most frequently is, I don't know how to start. Well, a good place to start is to find an equation that includes what you're looking for, okay? We're looking for the mechanical efficiency of the pump. So let's consider what that means. Remember, efficiency is just desired output over required input. What is the desired output of this pump?
400 kPa pressure difference.
Almost. Not a flow rate, not just the pressure difference. You're getting close. What form of energy does the pump put out? Flow energy, that's right. So another way of saying that is fluid power. Because we have to be careful, flow energy may or may not take into account all of it, because there's going to be a kinetic energy change as well, okay? Because of the area change. So that's the desired output. What's the required input? Mechanical power, right? The motor's job is to convert electrical power to mechanical power. The pump's job is to convert mechanical power to fluid power, okay? So let's just call that shaft power. Okay, now we're trying to find the efficiency, so we better figure out what's on the right? So how do we figure out the shaft power? Have we been given enough information to figure out how much shaft power there is? Yeah, sure. It's 90% of this, isn't it? Okay, so grab your calculator and take 90% of the electrical power. So let's call this W dot SH for shaft equals the efficiency of the motor multiplied by the electrical power. Because really the efficiency of the motor is just the ratio of those 2 things. Okay? So what do you get? 31.5 kilowatts. So that's how much power actually makes it into the pump. Thank you. Good job. So now what? Well, that takes care of this lower part here. How are we going to find the fluid power?
Well, we have a flow rate.
We have a flow rate. Good.
And we have a pressure difference.
We have a pressure difference. That's good. Will that account for all of the energy change?
Then we get balance, don't we? Bernoulli's would cover that.
Yeah, Bernoulli's in there somewhere,
Yeah,
right?
Bernoulli will cover that, I think.
Yes, it will, but we're going to use terms from this class, and we'll get something that looks just like Bernoulli's equation, okay? But the problem is that Bernoulli's equation doesn't include any power input, so we'll have to somehow deal with that.
Work going in.
Right, we have work going into it, right. So we've got to figure that out. Okay, now let's think about the fluid itself. What forms of energy does the fluid have as it comes into the pump? Is it at a temperature above absolute zero?
Yeah.
Yes, everything's above a temperature of absolute zero. What kind of energy is that? Thermal energy. So it has thermal energy coming in, it has thermal energy leaving. Do you expect the amount of thermal energy in the fluid to change significantly? Not unless you have a really crappy pump, okay? The purpose of a pump is not to change the temperature of the fluid, but to change the speed of flow, the velocity, not the mass, not the volume flow rate. It's incompressible, it can't change that anyway. But to change the kinetic energy essentially, and in this case, of course, the potential energy, the way it's drawn, and the flow energy. Okay, those are the 3 things, and that's why you guys suggested Bernoulli's, because you've been in 313 before or now, and you know that there's 3 different parts to head, right? There's pressure head, elevation head, and velocity head. And that's the same kind of thing here, same stuff. Okay, so you're on the right track. Let's talk about those 4 forms of energy. We already said there's probably not going to be any significant temperature change, so we don't expect to have to worry about thermal energy, right? That's out of the equation. How about potential energy? Do we know anything about the elevation change across this pump? No. Is it going to be small? Yes. Even if the pump is even if the inlet difference between the bottom and top of this pump is as tall as this building, that's probably still not significant by comparison to this pressure change and kinetic energy change. Now let's talk about the kinetic energy change for a minute. This is ideally an incompressible fluid, right? It's oil. So its density is not going to change. It's going to be constant. It's not going to shrink or expand. What that means is that the velocity exiting has to be different than the velocity coming in, right? How would we quantify that? Any ideas? We do it with something called the continuity equation. Do you remember in 220 when we talked about the fact that the mass flow rate, let's give these some numbers. Let's call this section 1, let's call this section 2. So the mass flow rate in section 1 equals the mass flow rate in section 2. It's basically a mass balance, right? This is a steady state. The rate at which mass goes in here equals the rate at which it leaves there. And then we realized we could write this in terms of densities and volume flow rates. But since the density doesn't change, we know that these two will just cancel. That means the volume flow rate at the entrance equals the volume flow rate at the exit. But we could even write that further as the velocity of flow. I'm sorry, I know there's too many V's in this class. This is the volumetric flow rate, this is the velocity of flow, multiplied by the cross-sectional area of flow. And remember that these velocities are average velocities at the cross-section, right? Yeah, I know there's going to be a flow profile, but we don't care about that right now. We're just interested in average velocities. That'll give us an average kinetic energy, which for our purposes is acceptable. Okay? So this equation is kind of nice because it relates the velocity of flow at the entrance to the velocity of flow at the exit. And you notice the exit has more area than the entrance does. That means there must be less velocity at the exit than at the entrance. Since there's less velocity at the exit, what does that tell you about the kinetic energy at the exit? It's gone down, right? It has decreased. We'll talk about this more once we're done with this problem. Anyway, so the kinetic energy we expect to be less here. Let's start to write some of this down. We expect to see some kinetic energy here and some kinetic energy here, and we already know this will be less kinetic energy than is in the entrance. Okay? But there should also be some flow energy. Okay? So how are we going to quantify flow energy? Well, at this point, what we should do is go back and look at the back of the chapter, and you'll see how useful the equation on page 97 is. Go to page 97, it's in the summary, and look at that little equation I pointed out last time that allows you to quantify the amount of energy that each unit of mass of fluid has. You see it? Little e sub mechanical equals P over rho plus V squared over 2 plus GZ. Now what is the GZ term on the end? What is that? What does it represent? Potential energy. We already threw that one away, right? So we're not even going to bother writing it. What about the other two terms? What are they? P over rho, what is that? Let's make it easy. V squared over 2, what does that represent? That represents kinetic energy, right? How about the P over rho? What is that? That's the flow energy, okay? So if we were to try and write something about this, we could make an energy balance around this. And we could go through the whole long energy balance that I went through last time, but we've already identified the relevant pieces. So let's just write it down. Because we know that the shaft power that comes in, if this is 100% efficient, should, excuse me, should change the fluid power like this. It would just be the mass flow rate through the pump multiplied by the change in the energy of the stream as it goes from here to here, right? The change in that mass, the energy that mass carries. We already identified is just going to be, excuse me, like that. You see what I did? I just combined the energy at the exit per unit mass with the energy at the entrance per unit mass. I took the difference between the two.
You can just have the times 0.9 to be inclusive there, can't you, for the efficiency?
That's a good point. Do we need the 0.9 here? No, that only talks about electrical to shaft power. That's done. We're finished with that.
That's not shaft power. Do we have a? No, we don't.
We don't. That's what we're looking for, right? Is that efficiency. Now, this is what we should get. Now, unfortunately, these two are going to be different things, right? because the actual efficiency of the motor is not 100%. Basically, this equation will not hold because there's also some heat loss. That's one way to say it, right? We don't know how much that heat loss is. If we knew, then this would be an equality, right? So what is this over here? Well, this is the fluid power. This is the fluid power that the fluid is actually getting. And I'd be willing to bet you it's not 31.5 kilowatts. I think it's going to be less than that. Does that make sense? So let's find out how much it is. All right. Now notice that fortunately we've already used a mass balance. And so we can calculate the velocity at the entrance and exit, and that'll take care of these two. So let's tackle that part first because we see that we need it. Okay, so let's make some notes here. The shaft power coming in is 31.5 kilowatts. That way I can get rid of this part. And I'll work with the mass balance. I don't need this bit anymore. This is the important part, right? So let's work with it. Now how am I going to calculate the velocity? Notice I don't have the velocity coming in, but I can get it, right? Because I've got the volumetric flow rate. And remember, this is all just the volumetric flow rate. So let's go ahead and calculate the two areas, A1 and A2. No, let's not do that. Let's just throw it all in at once. So V1 would be the volumetric flow rate divided by A1. V dot over A1 is pi D1 squared over 4. So this is 4 over pi V dot over D1 squared. Just writing down the algebra. Okay. So 4 over pi, the volumetric flow rate is 1/10 cubic meter per second, and the diameter is 0.08 meters, and we have to square it. Notice one of the things I do, one of the tricks I use to make this go smoother is if they give me something in centimeters or millimeters, I'll usually convert it quickly. That way I don't have to mess with units later. Okay? When you're staring at a problem and you're not sure what to do, you can start doing small stuff like this because you know you're going to have to anyway. Okay? And that'll save you some time, especially on a test, and kind of get your brain in gear and you stop panicking, you start working, and everything comes out. Okay, hopefully. Right? Okay, so plug this in your calculator, please. What kind of velocity do you get? And notice it'll work out because we'll have meters squared in the denominator, meters cubed in the numerator per second. That'll give us meters per second, which is velocity. So grab your calculator, please, and tell me what velocity you get for the entering stream.
$19.89.
19.89 meters per second. Anyone agree with that?
I agree.
Okay. So there we have it. So let's jot it down over here. V1 is 19.89 meters per second. Okay, now let's take care of the exit. Now, to calculate the exit, I'm going to do something slightly different. What I'll do is I'll just rearrange this one. Watch what happens. V2 would be equal to V1 A1 over A2. All right, just moving the A2 over. But this would be V1 and the A1 being pi D1 squared over 4 over pi D2 squared over 4 is the A2. Pi and the 4 go away. Okay? And so we can even simplify this a little further, say it's V1, write a little better. V1 D1 over D2 quantity squared. We might be able to do some of this in our heads. This would be V1 D1 over D2 is going to be 0.08 over 0.12. No, I guess not. All right, let's go ahead and plug it in then. 19.89 meters per second multiplied by D1 is 0.08. D2 is 0.12. Has to be squared. We don't have to worry about units because they cancel. So what do we get?
8.84.
Yep.
8.84, okay, thank you. Meters per second. So there's our velocities at the entrance and exit. Okay, so we've used up this equation, we don't need it anymore. Let's get rid of this part as well, so we can do some more work. The other thing we're gonna need is this mass flow rate. So let's consider it. Remember I said the mass flow rate can be calculated as the density times the volume flow rate, right? These are pretty handy things to kind of commit to memory, okay? So the density is 860 kilograms per cubic meter. The volume flow rate is 1/10 cubic meter per second. And you can do this in your head and say that the mass flow rate, let's just do it here, m dot is 86 kilograms per second. That was an easy one. Okay, this is just a 10th. Okay? Now that we've got all that, whoops, let's tackle this thing. So this is the actual fluid power. So the fluid power then, we use sub FL W dot for fluid power, is the mass flow rate, which we know is 86 kilograms per second, multiplied by P2 less P1. Well, P2 is greater than P1, and that difference is 400 kilopascals, and we have to divide that by the density, 860 kilograms per cubic meter. So that takes care of this first term. Okay, we have to add to it V2 squared, so that's 8.84 squared, less V1 squared, which is 19 point, I hope I have space for this on the video, 89 squared, divided by 2. Now we have to be careful here. The units of this whole term would be meters squared per second squared, because we've got two different velocities that are themselves squared, right? How about the units over here? What are they? What is a kilopascal per kilogram per cubic meter? Any ideas? There's a handy conversion factor you need to commit to memory, but you don't have it yet. So go to the back of your book and look up pressure. I think they've got it in here somewhere. Well, I don't see it.
What'd you say it was?
I was looking under pressure. You know what? I think actually I'm having a short circuit in my brain. I'm thinking of the kilojoule to kilopascal times cubic meter conversion factor. You guys may not remember that, but we'll come to that one later. Let's play with this and see what we get then. So a kilopascal per kilogram. Now let me put the cubic meters in the numerator. I just converted and multiplied. And let's see, a kilopascal would be a kilonewton per meter squared, right? Because a newton per meter squared is a pascal. But a newton is a kilogram meter per second squared. Okay, so the kilograms will go away. And what else? Let's see. Okay, we've got meters to the fourth power here, divided by meters squared. So let me just do that. So we'd have kilo, or 1,000 meters squared per second squared. Does that make sense? It's gotten kind of messy. Did you get to follow it or not? Notice what's happened here. The kilograms went away. I've got meters times cubic meters, which is meters to the fourth, divided by meters squared. So that's meters squared that
And
remain.
that should be divided.
No, that's multiplied. That's meters squared per second squared. Let me expand it a little bit. I can see you guys aren't following. Let's try
So
it
many
again.
denominators.
Let me make it bigger. Maybe that'll help. Kilopascal per kilogram per cubic meter. Is that okay so far? Can I put the cubic meters up here?
Yeah.
Let's do it. That gets rid of them down here. I need something to get rid of that kilograms. It's going to have to come from here, right? What is a pascal?
Newton kilogram per second squared. No.
It's a newton per meter squared. That's a pascal. Okay. What's a newton?
Kilograms per second squared.
It's a kilogram meter per second squared, right? Can I cancel the kilograms?
Yes.
Right, because this is in the numerator of the denominator, invert and multiply, kilograms are gone, right? Now I can get rid of that because it's over 1 and that's understood, right? Now let me simplify a little bit so you can see this. Right? I can invert and multiply here, right? So what I'll have is, let's see, meters per second squared times meters squared. Let me just erase this. Well, let me write it down so I don't mess it up. So we're going to have meters per second squared, that's up here, and we're going to have meters squared over 1 when we invert and multiply.
Wouldn't it be 1 over meter squared? 'Cause the meter squared is over 1 right now.
You're right, thanks. I'm not thinking right. So it's going to be 1 over meter squared. Thank you. I would have gotten to the end and wondered what the heck happened. Where did I go wrong? Okay, so now we can cancel that, right? So basically this piece here just becomes 1 over meters seconds squared, right? Okay, so that takes care of that. Now this 3 looks like it's multiplied, it's supposed to be cubed. This is in the numerator, and really we could move it over here and say it's just meters cubed, right? This will cancel 1, but we'll be left with the meter squared. Now does it make more sense? So we have meters squared per second squared, but wait a second, there's 1,000 of them. So this, the number here, is 1,000 of the number here, right? And since we'd like power in some units that we recognize, why don't we get rid of this K? Why don't we just notice that we need to multiply 1,000 here? Basically, we need 1,000 there because there's 1,000 meters squared per second squared for each kilometer squared per second squared. Does that make sense? That's where that 1,000 comes from. All right. Let's see. Yeah, that should do it. So grab your calculators. And by the way, one more thing. Notice that this term is positive, right? There's an increase in the flow energy. Notice this term is negative. There's a decrease in the kinetic energy. That's what we expect. Okay? So just for the fun of it, to compare okay, there's not really any fun in thermo, but for the sake of discovery, calculate this term separate from this term and give me numbers for the two. Let's see how big they are. So 400 over 860 times 1,000 is how much? It's going to be about 500.
Yeah, 465.
465 point what?
1.
Okay, good enough. And that's meters squared per second squared, because we've already taken care of this 1,000. And what's this one? 8.84 squared less 19.89 squared over 2. How much is that?
Negative 158.7.
So they're appreciable, right? They're similar, but this one is about 3 times this one, right? So the flow energy increase is about 3 times the kinetic energy decrease. Okay? Now let's multiply it all out. Get rid of this. So finally, 86 kilograms per second multiplied by 465.1 less 158.7 units are meters squared per second squared. Okay. What number do we get? I'll let you guys work the number first and then we'll figure out the units.
26,350.4.
Okay, so let's leave it at that, 26,350. But what are the units? Well, we've got kilograms per second times meters squared per second squared. All right, let's see what we can do. We don't need, I guess we don't need this anymore. So I tell you what, I worked the units last time. You tell me what to do with these units. What should I do? Tell me what to write.
Just using units,
Yes, just the units.
so kilogram over second,
Kilograms per second.
multiplied by meter squared over second squared.
Good.
Yeah, that's it there.
Okay, so now what do we do?
Kilograms times meter squared over second.
Yeah, we have kilogram meter squared per second cubed, so what do we do with it?
Yeah, that'll be a four, so that'd be.
The first thing to do is to try to find a newton in there somewhere, okay? We're gonna have to use the kilogram to get a newton. So how much is a newton? It's a kilogram what?
Meter per second.
Meter per second squared, right?
Yeah.
So we can use this second squared with this kilogram and one of these meters, so I won't copy the square, right? And that'll become a newton. So if this goes away, it'll become a, in fact, let's just write the whole thing. Let's
And
say
then Newton times meter
Newton, meter
per second.
per second, right? What is a Newton meter per second?
Pascal.
Well, not quite. What's a Newton meter? A joule,
Second to watt.
which is a watt. There we go. We're trying to get to kilowatts, right? But we've got watts. How do we get kilowatts?
Divided by 1,000.
Okay, so this is 26.4 for all practical purposes, kilowatts. Okay? So 26.4 kilowatts. How much did we put in again?
31.5.
So how much we got out? Where's most of the loss? I don't know. Let's see what the efficiency of this thing is. We've just calculated the fluid power. We found that it's 26.4 kilowatts. So let's calculate the efficiency. Fluid power, 26.4 kilowatts. Shaft power in, 31.5 kilowatts. What do you get?
We got 8.3%. 8.4.
You mean 0.84?
I think I had a decimal point wrong, so hang on.
I think so.
Yeah.
So 84% or so. So the pump loses more energy than the motor does, right? It's more lossy because there's not a huge difference. The motor's at 90%, this is pretty darn close. But there's the answer that they were looking for, was at 84%. At least that's what we got, unless we made a mistake. I got 83.6%. But then I plugged a lot of symbols in before I put in numbers. Okay. All right, now, something else to talk about here that's practical. Anybody ever worked with a pump before? Well, did you know that the outlet of a pump is usually smaller than the inlet? You know why? Most of the time you're dealing with centrifugal pumps. Centrifugal pumps are basically just blades that are kind of like a lacrosse thing, right? You got a stick with a basket at the end, you throw it, right? Well, that's basically what an impeller is like with blades on it. It's basically just pushing against the fluid and throwing the fluid outward is all it's really doing. So pumps like that are really good at increasing the kinetic energy of the fluid, but not necessarily the pressure, the flow energy. And so one thing you commonly do, you commonly have a smaller exit. And what will happen is you'll go ahead and use an expander, or the opposite of a reducer basically, to expand it back out to the same diameter usually is what comes in. But what will happen is that in that expansion, we'll find this out a little bit later, it's basically a diffuser. What will happen is you'll get what's called pressure recovery. Some of the kinetic energy will be converted into pressure. So the pressure will actually go up as you're moving downstream, which seems counterintuitive. But basically it's converting the kinetic energy that the pump generates into pressure, which is usually the reason you make a pump anyway, is to generate pressure. Okay? Questions, comments?